Okay. Audio. Okay, it is time to start. Want to remind you again that chapter 19 requires more attention because multiple new terms are introduced, and also the discussion in the textbook is not perfect because we don't have the tools of calculus. So keep in mind also that even though the official textbook that we have is a good book, you can use practically any textbook that you have. The material is pretty much the same. Even most of the problems that you're going to encounter are either identical or very similar to the problems from our textbook. So keeping that in mind, let's start with a summary of where we stand. We started, of course, with Coulomb's law, and after that we started introducing terms that are specific for electrostatics. So I started with Coulomb's law. And after that we said, well, if one of the charges in Coulomb's law, let's say, is positive, we call it test charge, and the force divided by the value of that test charge, let's say Q2, we call electric field at the place where that test charge is located. When you combine the two formulas, we figured out that the magnitude of the electric field at a distance r from a source charge Q1 is given with k times Q1 magnitude divided by the distance squared. After that, we introduced geometry because the formula that we have, for example, for the electric field created by a single charge Q1 in magnitude given with this expression, and the direction of the electric field given with the definition, we said that we describe the electric phenomena generated by a source charge Q1 in terms of the electric field created by that source charge. At every single point in space, the formula describes a vector, electric field vector, generated by the source electric charge. In a similar manner, you can analyze electric fields generated by multiple charges, point-like charges or even extended charges. At every point in space, you attach a vector representing the electric field vector, and this is sufficient description to tell you everything that is going to happen from electrostatic point of view in space. Well, after that, we started thinking about energy stored in a configuration of electric charges. And for simplicity, the formulas that we analyzed was the electric field stored in a configuration of two point-like charges. Maybe positive, positive, or maybe negative, positive, or negative, negative. And we made an argument, which was not, of course, you can argue that it is an experimental result because we don't have the tools of calculus, but we made the assertion that the energy stored in a configuration of two point-like charges separated by a distance r is given with a simple formula, a product of the charges divided by the distance between them. Very simple expression. Electric potential energy stored in this configuration of two point-like charges, which is the simplest possible configuration if you think about it. Keep in mind that in this formula, the electric charges Q1 and Q2 have to be taken together with their algebraic sign. And the result may be electric potential energy that is positive or negative. Now, let's say that one of the charges is positive, just for the sake of the argument. Let's say Q2 is positive. You define electric potential, or what I call voltage, as electric potential energy per unit charge, per unit test charge Q2. Right? We said, let's make Q2 positive, so call it even test charge, and here it is our definition for voltage. Strictly speaking, instead of voltage, we use the term electric potential, but to distinguish it from the multiple other electric terms, I'm going to use the concept, the word voltage. So units, of course, joules per coulomb, and joule per coulomb is what we call volt. Unit for electric potential, for voltage. Now we have to realize that electric potential energy is exact analog of gravitational potential energy. The difference is very small. And when we talked about gravitational potential energy, we said that the gravitational potential energy is defined up to a constant. It is defined up to whatever you take for zero height. So gravitational potential energy of this object here is mgh, but h is the height with respect to whatever 0 point you have taken. If you take the 0 point of the height to be the surface of the table, mgh here is 2 joules of gravitational potential energy, because this distance is appropriately 1 meter or whatever the distance is. But if you take the 0 point, let's say to be the sea level, the gravitational potential energy mgh of the same object located on the same spot is going to be 1,000 joules instead of 2 joules. So energy, potential energy in general, is defined up to a constant. And that constant depends upon where you have selected the 0 point. Exactly the same situation you have with electric potential energy. Depending upon where you choose the 0 energy to be, the electric potential energy can have any value you want. Well, very often we forget to specify the 0 point location for electric potential energy? Well, as a convention, when nobody tells you where the 0 point is, we assume that the 0 point is either infinitely distant from us, at the end of the universe somewhere, where there are no any charges or anything else. And equivalently to that, we also take the 0 point to be also the ground, the planet Earth, the ground of the planet Earth. So we cannot. So let's talk about now this voltage. Now, you may say, well, we have a substantial level of arbitrary choice here. Do you choose the 0 point of electric potential energy voltage to be this point, or do you choose it to be this point somewhere there? And depending upon, you may feel very uncomfortable, because depending upon where you choose your 0 point, the solution of your homework problem may be either the number 5 whatever units, or it could be the number of million whatever units. Luckily, that doesn't happen. Luckily, it can be proven mathematically that in any physical discussion, the result and also the input for the 0 point just doesn't matter, because the answers only depend upon the difference between electric potential energy of 2 points. So the difference of 2 heights is the same number, no matter if you select the 0 height to be here or you select it to be somewhere else. The difference is the only thing that matters. The same story is valid for electric potential energy, and therefore for voltage, because voltage is nothing else but electric potential energy per unit charge. So when you last time we started talking about that, but let's make sure that we understand it. Here is battery, right? How many volts is this battery? 9, clearly. Okay, in that case, what is the voltage at this terminal of the battery?
4.5.
4.5 plus or minus? Okay, 4.5. What about the voltage on the other end, on the other terminal? If this one is 4.5 plus, this one should be 4.5 minus, so the difference to be 9 volts. But very often, if you look at this battery connected to some device, you're going to see that one of the terminals is connected to the ground. And you may start worrying that you are losing half of the energy stored in this battery, because half of the current kind of goes into the ground, kind of. Right? This is a reasonable assumption. In reality, nothing like this happens. You cannot say that if this is a battery not connected to anything, you cannot say that this terminal is 0 and this one is 9 volts. You cannot say that this terminal is positive 4.5 and this one is negative 4.5. Well, you can say it, and it may be accurate. But the exact statement, if I say that this terminal is 1,000,000 volts, and this terminal is 1,000,009 volts, This is going to be perfectly accurate statement. What matters is the difference between the voltage at this and this terminal. This is what matters. In other words, the batteries and all other devices that create voltage, they create voltage difference between 2 points. They don't create a voltage at certain point. So I can connect this terminal to the ground, make it 0 by convention, right? We said the ground is a convention. The other terminal immediately is going to jump and become 9 volts. Perfectly fine. That I'm not going to lose half of the energy of the battery, and it's just going to work perfectly fine if I do that. Okay, so keeping this in mind, and keeping in mind that in every problem solution, only voltage differences are going to appear, let's analyze a little bit the energy, again, stored in a system of 2 point-like charges. So you have 1 point-like charge here at point A, another point-like charge here at point B. We already know that the amount of energy, well, let's make this one Q1, Q2. For simplicity, let's make both of them positive charges. Doesn't matter. We know that the amount of energy stored in this system is given with this expression. Just multiply charges divided by the distance between them, and you have how many joules are in the system. Now, you can assume that the voltage at this point A is some number, VA. We can assume that the voltage at the other point B is some voltage B. And now, let's do the following exercise. Let's think how much work a person has to do in order to bring Q1 from point A to point B on top of the other. Well, you have the work to move from point A to point B is going to be equal to the change of electric potential energy, right? Energy is conserved. Change of energy is equal to work. But change of electric potential energy is going to be electric potential energy of the system when the charge is at point A minus electric potential energy when the charge is at point B. Now divide, so now keep in mind that in the textbook you have a minus sign. And that minus sign is because you're expressing not the work done by the external force to move the charge Q1 to point B, but you're calculating the work done by the electric forces that are in opposite direction, repulsive forces in opposite direction. So this is the origin of this negative sign. You're calculating the work of a different force. So if you calculate the work of the electrostatic force against the external force, that work is going to come out negative, right? The electrostatic force is this way. The displacement is in opposite direction. Work is force times displacement times cosine. The cosine is cosine of 180. Cosine of 180 is -1. So you end up with this minus sign. Now divide both sides of this expression to the value of the charge, let's say Q1. And you're going to get work divided by the charge is equal to electric potential energy at this point. Well, okay, at configuration A, let's say, divided by the charge minus electric potential energy at configuration B divided by the charge. But this is voltage at point A. This is voltage at point B. In other words, you get that the work in magnitude per unit charge is equal to VA minus VB. Here it is, a difference of voltages appeared. This is difference always has to appear. So very often, difference of voltages you denote with delta V. And sometimes you even forget the delta sign. Sometimes in the textbook, you just forget. You always keep in mind that when you say V, you mean difference between voltages. And the result now looks like this. The work done by the electric forces is equal to the voltage difference between the points, between 2 points, multiplied by the value of the charge that moves between those 2 points. So often we're going to use this formula to calculate the work done either by electric forces or to calculate the work done by external force. In that case, the minus sign disappears. You don't need to remember where you have this minus or plus sign. You just have to look at the diagram and see if the direction of the force that you want to find its work is opposite to the direction of the displacement of the charge, you have minus sign. If they're in the same direction, you have plus sign, and everything is going to work just by looking at the diagram and not worrying about who does the work and on which system the work is done from outside. So now let's look at what we said so far from a more general point of view, without worrying about works and minus plus signs, products, deltas, and so on. When we introduced the concept of electric field, we said that that concept allows us to forget about the source, but think about a vector attached to every point in space. A vector with magnitude of electric field and direction described with words. So we said, for the simplest case, let's say when you have one single positive charge, let's say Q, at this point, you attach a vector representing the electric field at that point created by your source, like this. At this point, you attach a different vector, again, according to the formula that describes the magnitude and the direction of the vector with words. And it gives you a very complicated map with infinitely many vectors. Every point has a vector attached to it. This is our description for electric field. For simplicity, we said, well, let's connect the electric field vectors at different spots that are roughly in the same direction with continuous lines. And the result was electric field lines description of the same electric field. simpler to draw, at least for the case of a single source charge, positive in this case. The electric field lines look like this. Well, now we have an alternative. Now we can combine this in this formula very easily, right? Substitute electric potential energy with this expression. Q2 is going to cancel, and you get that the voltage created by a single charge Q1 is the charge divided by the distance times K, the same constant. So practically this formula tells you attach to every single point around your source a scalar number, the voltage created by that source at that position, at that distance. Yes.
Yeah. In some of the equations you have Q1 and some you have Q2. Are those all just referring to test charges, or is Q1 something specific and Q2 something specific?
So Q1 and Q2 could be either positive or negative, and it doesn't matter if you take what combination of algebraic signs you take. So for consistency, I take Q2 to be positive, but I don't have to.
So they're all test charges.
Well, one of them is test, one of them we name test charge, the other one we name a source charge. So for my formulas, Q2 is test and Q1 is source. So Q1 is the source, and the voltage created by that source at a distance 5 meters is Q1 divided by 5 times K. Very simple recipe. That recipe tells me that I can attach at every single point a scalar number, the voltage. It is a number, simple number, positive or negative or zero, simple scalar voltage. And now I have another map where at every single point a number is attached, the voltage at that point. Well, again, it is more convenient to simplify this map with infinitely many numbers. So if you have, let's say, according to this formula, let's say you calculate that at this point, the voltage here is 5 volts plus for definiteness. Well, if you calculate using the same formula, the voltage at this point, you also are going to get 5 volts if you're at the same distance from the source. And so the set of all points with the same voltage in them, you can call equipotential surface. And it is clear that for a single point like charge, the equipotential surface 5 volts is a spherical surface like this, with center at the source. After that, you can connect all points that have voltage of plus 2 volts, like this one. All the points that have that voltage form another equipotential surface that we call plus 2, and so on. So you have a set of equipotential surfaces. And therefore now we have 2 alternative descriptions of the electric field created by a source Q1. Either description of electric field in terms of electric field lines, or a description in terms of equipotential surfaces. Of course, description in terms of equipotential surfaces should be simpler because the potential, the electric potential that forms this equipotential surfaces is a scalar number, doesn't have direction. While the electric field lines go with direction, and working with vectors in general is more complicated. Well, let me show you the electric field lines and the equipotential surfaces. If the field is created if the field is created by, let's say, a single charge, maybe, let's see. So electric field lines created by a single charge are with red, electric field lines. Is the source positive or negative charge? Well, when you look at the direction of the electric field lines, it becomes that it is positive source, right? Electric field lines originate either from plus or from infinity. So they originate from positive charge. And here is the equipotential surface plus 30 volts, spherical surface. Equipotential surface plus 20 volts, equipotential surface plus 10 volts, and so on.
So the volts are always strongest the closer they are to the source point, right?
So, well, the question is where you have higher potential and where you have lower potential. Well, in magnitude, closer to the source, you're going to have in magnitude higher potential. But you're going to encounter cases when the source is positive and the potential somewhere close to it is -5 volts, let's say. It may happen because, remember, the number of volts is defined up to a constant. Here we assume that the constant is 0 at infinity. But in other cases, that assumption is not going to be valid. So yeah, closer to the source, you get higher magnitude of voltage. But is it positive or negative? You have to be careful. And now look at the electric field map generated not by a single charge, but by two charges, two sources. One positive and one negative source. Maybe with equal magnitudes in this case. Again, with red, you have electric field lines. Description in terms of electric field. With blue, you have equipotential surfaces. And notice that the surfaces here are not spheres. So maybe this almost spherical, but not exactly spherical surface could be plus 5 volts. This one may be plus 1 volt, plus half volt. This surface may be -5, -2, and so on. The green surfaces, those are cross sections, they are three-dimensional surfaces. And this equipotential surface actually is going to be exactly 0 volts if the two charges are equal in magnitude and opposite direction as they are. So when you are analyzing equipotential surface map, a good analogy to voltage would be height. So exactly like electric potential energy is similar to gravitational potential energy, exactly the same way voltage is similar to height above table or above sea level or whatever. So let me show you the equipotential surfaces for the height. They're familiar. So here is equipotential surface. Well, strictly speaking, the equipotential surfaces are flat surfaces here, or almost flat surfaces, but their intersection with the terrain gives you the map here. So this is 10,400 feet equipotential surface. This one is what, 10,200 or whatever. Right? Each line represents equipotential surface cross section with the terrain. Exactly the same way you have the equipotential surfaces created by electric charges. Okay, so with this in mind, let's look at the following situation now. We have two alternative descriptions of the same situation. Electric phenomena can be described in terms of electric field or in terms of electric potential. Electric field is complicated vector, 3 times more complicated than scalar voltage. When you have two different descriptions, two different languages, you need a dictionary. Well, it is nice to have a dictionary to allow you to go from description of terms in terms of E to description in terms of V. It can be shown, and again in the textbook it is not strictly shown, that the dictionary is a single, very simple formula. The dictionary says the electric field in magnitude is equal to the change of voltage when you make a step with size delta x, the minus sign, which for you is not very useful. But this formula, again, is important because it is a dictionary between two languages, English and Sanskrit or whatever, right? Two different languages. If you have a dictionary that is a single formula, that's priceless. Writing the exact dictionary formula without calculus is a pain because you have to use also many words. Because electric field is a vector and this formula doesn't involve vector notations. So without calculus terminology, this formula is valid when the step size from one point to another to the other is infinitely small. In other words, the 2 points have to be, in general, very close to each other, infinitesimally small step delta x. On top of that, this formula works perfectly well only when the step delta x is taken along the electric field lines. If you want to take a step not in the same direction as the electric field lines, you cannot directly use this formula. You have to talk much more. The minus sign again allows you to determine the direction of the electric field. But when we do examples, I'll show you how to determine the direction of the electric field without using minus plus signs, just looking at the configuration that you're involved. And this is going to be simpler and preferable, so you're never going to make a mistake. But I'll keep this minus sign just not to write wrong formulas on the board. Again, you're not going to use it explicitly. Okay, let's see questions and remarks.
What is the X represent again?
X, delta X, is a step size.
Oh, right.
So it is a distance between 2 points. Delta X is a distance between 2 points. Delta V is the potential difference between those 2 points, voltage difference between those 2 points. And a lot of working to tell you that you're only allowed to make the step delta X along the direction of the lines, along the line rather than on the side. Okay, well, now, one property that we also have to keep in mind here when you look at the electric field lines, the red lines, and the equipotential surfaces, one important property is that electric field lines are always perpendicular to equipotential surfaces. You see that they're perpendicular, right? Red is perpendicular to the green. The same thing in the next map. Always perpendicular, red to green. No other option. This is one property of equipotential surfaces. The other property of equipotential surfaces is that metals are equipotential surfaces. No matter if they are charged electrically or electrically neutral, this is equipotential surface. Since I'm touching it with the ground, that equipotential surface right now is exactly 0 volts by convention. It is the potential, the voltage of the ground. If I charge it, it is going to be equipotential surface of, let's say, about 1000 volts. Now, a useful number maybe to keep in mind is this. Let's make them. So I'm separating. So this is grounded again, right? It is connected to the ground. This one is grounded, but this one is not grounded. Let's charge it. So when I start putting charge on it, the voltage on it is going to start getting 100, 200, 500 volts. And the voltage on the surface, of course, on the second metal sphere is going to be 500, 1000, as much as I charge it. Look, let's charge. Let's keep charging it. You see that when the potential difference between the two spheres reaches some value, you observe sparking. The reason for the sparking is the presence of ions in the air, small number of ions, and those ions get, let's say, positive ions get accelerated away from the positive into the 0 voltage sphere, and the result in the process of this acceleration, they ionize more air molecules, and you observe this ionized stream of air molecules as a spark, the stream of moving molecules. In order you to see the sparking, the voltage difference between the 2 points has to be between 10,000 volts and 30,000 volts. This is the voltage difference between 2 points separated by a distance of 1 centimeter. You need for a spark. Well, is it 10,000 or 30,000 volts for every centimeter of separation? Depends upon humidity, temperature, atmospheric pressure. So the number differs between 10,000, 10 kilovolts and 30 kilovolts per centimeter, depending upon the conditions of the air. So let's discharge it. Got surprises. Okay. Well, you realize that there is energy stored when you have electric charges in space, in the system of electric charges. 2, 3 electric charges carry, the configuration of those electric charges carries energy. And energy is something useful, right? Because if there is certain amount of energy, you can convert it into work. It can do work for you. It can turn the wheels of the car, or it can warm you up in the winter. So work and energy are the two sides of the same coin. You want to store the energy and convert it into work whenever it is needed. The question is how to store this electric potential energy. And, well, how do you store it? Take a bottle, a jar, and put the electric charges in this jar. This is what people did first. They used actually glass jars, lighted jars, whatever they called them. Gradually, they realized that you don't need the shape of the jar to store the electric charges. The simplest shape that you need, that you can use, is 2 metal plates. Always one of them charged with positive, the other one with negative electric charge, equal in magnitude charges, but opposite in sign. And this system is a simple system that stores electric potential energy, stores energy. And that simple system that I just broke is called parallel plate capacitor. Yeah, we're going to repair it because it is a useful tool. So we have to calculate now the energy stored in a parallel plate capacitor. Yeah, I'll deal with it later on. Just imagine 2 plates. So now, since those are metal plates, if this charge here is positive Q, that charge is uniformly distributed on the surface. And traditionally, as we saw last week, we describe the amount of charge stored on a plate with surface charge density sigma, charge per unit area of the plate. Okay, so I probably have to stop here because we're out of time. So next time, we're going to talk about energy storage, capacitors, and energy in general contained in any electric field configuration. And this is going to conclude the discussion of chapter 19. Look at the homework problems. We have to do some examples of your choice in order to demonstrate the uses of the algebraic formulas and the appropriate selection of algebraic signs. And if you don't have questions for next time, I'm going to show a few slides with conceptual questions as in a form of a quiz on the screen again. So